Hello, everyone. I am Joshua Metchler from Serial Cable, the local field applications engineer. We will be doing a power analysis Quarch demo today. And for that, I will hand off to Andy Norrie, the co-founder of Quarch. And he will answer all of your questions. If you do have any specific questions, please put them into the chat section and we will handle them one by one. Andy, the floor is yours.
Thank you, Josh. So thank you for joining us. We are talking about power analysis today, specifically around the Quarch solutions. Obviously, a lot of you will know serial cables. So if any of the stuff that we see here is something you want to try out, then these guys will be able to get quotes or evaluation units or anything else you need. So briefly to go this, we'll start a little bit about Quarch for anyone who hasn't come across the company before. We'll then look at the range of power analysis products and solutions that we actually have. We'll then go a bit into Quarch Power Studio, our main analysis application and what it can do. And then we have a look at some of the latest hybrid power and breaker products that we've got, and a little bit about automation in terms of how you can make these products work inside your existing automation system. So a little bit first on Quarch, the company. So we were founded in 2006. We are based in Scotland, in the UK. All the products that we make are designed, built, and tested in the factory here. So there's no drop shipping from other locations. We work with pretty much every major storage company in the industry, and we've been branching out recently into a wider range, especially around power. It's a very major requirement for many companies now, understanding the power consumption of their products. We work with high quality partners such as serial cables in every region, so you guarantee to get fast support. We've got a very good reputation with our customers, both in terms of our products and direct technical support that you get. And one of those points is that we have direct engineering support to our customers. So if you send in a query ticket in, it will be seen by all the senior engineers working on the products, and hopefully that means you'll get a very fast solution. So there's a couple of ranges of products that we work with. The one we're talking today is our power analysis range, and a little bit into the compliance testing side as well. We also have a range of hot swap and fault injection products that were the original Quarch products. So there's a wide range of other things that you may want to look at in the future as well. So starting off with a bit of an overview of power analysis. When we came into this industry, we find that traditional testing generally required, if you want to test a single drive, you need oscilloscope, you need calibrated current probes, you need 2 voltage probes, you need custom cabling and fixturing to get everything set up together. And if you want to actually do supply testing into the drive, you need a dual rail programmable power supply. That's a lot of equipment to put together. Potential problems are the normal missing equipment, incompatibilities, the problems of complex setup. In terms of AC measurement, there's a lot of potential dangers involved if you're actually having to wire up equipment. It can be very difficult to automate, especially if the kit you have is coming from different vendors. And there's a major risk of mistakes, and we've seen time and time again setup mistakes, getting the wrong results, and then of course spoiling all the work that's done. Some examples of this here from customers. We've frequently over the years been challenged over our power measurements in comparison to DC power analyzers, scopes and current probes and similar. And in basically every case, we've been able to demonstrate that our values are correct. So one here from an enterprise drive manufacturer indicated that with our equipment, they were measuring their drive's idle power as 25% higher than with their previous method of testing. And after some back and forwards, the customer came back and said they verified, and they were measuring the voltage and the wrong pins on the board in their sort of wired up test fixture, and as a result the idle power they were measuring wrong, and it was in violation of their own spec, which is a serious problem. The devices that they were shipping did not meet the spec that they claimed, and this was just due to the complexity of the test setup of getting probes and things in the right place. And again, another enterprise drive manufacturer saw a 28 milliamp difference between the Quarch product and their current probes. And again, after a fairly significant debugging effort, we found that they had a DC offset setting on their probe that wasn't calibrated correctly. And again, The ppm was correct, the Quarch product, the current probes were not. Finally, just a couple of months ago, we had a customer who was objecting to the measurements on our programmable power module. And in this case, it turned out actually to be unit-to-unit variation on the DC power analyzers they had. So they were just inconsistent with the equipment that they had. And again, in the end, that they were satisfied that the measurements we were giving them were in fact correct. And a major reason for that is the design of this. So basically, all the equipment that I showed before in the Quarch product range, this is our programmable power module, is combined down into one small unit. So this is a combined unit it's a dual rail programmable power supply with measurement and with plug and play fixtures all together. So you can see the simple setup on the bench here. We've got a fixture to go between the drive and the host, plugs into our power module. The power module is connected on USB to our host, and then we're up and running, measuring power and voltage in a matter of seconds to plug this together. And the chances of getting it wrong are substantially less. So as an overview of the product, this is we have a single and a 6-port output model. Both are intended to be the same thing. One simply has more ports. Each port is designed to power one drive. That can be SAS, SATA, or an NVMe based drive. We can support both 3.3 and 5 volt rails. And we have fixtures for a very wide range of different devices. So we aim to cover every major drive standard and a number of others. So whether it's U.2, U.3, SAS and SATA, or it's the latest EDSFF E3, we can supply power into pretty much every standard interface. And again, this is a very quick setup. Although if you have your own custom wiring harnesses, we have pluggable screw terminal fixtures, Molex and similar as well. So with this, what you get is a very simple piece of test equipment. We have USB and LAN control. We've got advanced cross-platform applications and simple automation options to get you the measurements you need for pretty much any drive. So we can measure we spec'd down to 100 microamps. In practice, with our latest FPGA that we're about to release, it's more like 10 microamps. Although we're still working on the exact levels for that. So basically, we can measure from low current sleep states all the way up to high inrush currents. And we can do so at up to 250 kilosamples per second with a high level of accuracy. So for low power sleep states, we're talking about 2 microamps plus 2% error. And at higher power states, we're roughly 2 milliamps. So this is very comparable with other pieces of test equipment. It will get you the data you need to qualify your drive in detail. The power supply can also slew from 0 volts to nominal plus 20% at very high speeds. We can do roughly 1 volt per microsecond. We have 1,024 pattern points, so we can create a series of complex patterns, ramps, glitches, brownouts, and similar. So a very wide range of different output tests. So for instance, does the drive work at the extremes of voltage ranges as specified on its input, normally plus or minus 10%. Brownout, does the drive shut down cleanly if the voltage rail drops slowly? What about if it drops very fast, a hard pull down to ground? Or glitches, how does it respond to brief interruptions in supply? What's it going to do? And the examples we can see here on the left, we're pulling down each of the 2 rails at slightly different times to different intermediate voltages. And on the right hand side, we've created a little bit more of a complex pattern with both rails ramping up from 0 up to their nominal voltages, but we've taken some glitches out of the 12 volt rail to simulate other high power devices coming onto the power supply and pulling the rail down briefly. So with this, you can create a very wide range of active power tests. But of course, this unit does a lot of measurement side as well, which most of our customers are using all the time, and we'll look at that shortly. We have a second range of products called the Power Analysis Module, or PAM. This was actually the winner of the Most Innovative Sustainability Award at this year's Flash Memory Summit, which was fantastic for the team. This is a very similar product. The difference here is we're not supplying power. This is measurement only. So in this case, we've got a range of plug and play fixtures. You can see there's an AIC slot fixture here on the image. In this case, we're supplying power into I think it's a QSFP host card. So again, we can measure power on just about any device, whether it's a storage device, a graphics card, AI accelerator, or similar. Because we're not supplying power here, we are looking at the actual interaction between the host and device. And at the same time, we can also, because we have these now, we have an active interposer card, we can capture digital signals as well. So as well as looking at the power rails going through, we can also capture things like burst assertions and clock rec. There's an improved architecture that was behind this. So instead of supporting just 2 channels, as we had with the programmable power module, the PAM can support multiple different voltage rails and multiple different digitals. And that allows us to produce not just devices for pure storage, but in the bottom left here, we can see our 2-channel power analysis fixture. So this has 2 analog rails, which will run up to 15 volts. And it also has 16 different digitals. So this is basically turning the whole product line into almost like a mixed signal scope at the same time. As well as, of course, of doing your standard U.2, U.3, M.2, EDSFF, and similar devices as well, if you don't require the ability to actually generate power to your drive. Now, this is just at the drive level, but what do we do as we scale up? Drives are only one part. We've also seen more and more need for server power usage, and then entire racks, other IT equipment. We also have customers interested in power quality, for instance, on failover. What is the quality of the generator supplied power? How fast does the UPS switch over on loss of external power? And then we've got the upcoming energy standards, SNEA Emerald, for instance, and various other bodies around the world are starting to look at data center energy consumption and set fairly strict standards on how much power is used and on measurement of that. So the PAM range has expanded from just DC measurement of drives and slots-based PCIe cards up into the mains realm as well. So what we have here on the bottom is our 3-phase PAMs. This comes in 16, 32, and 63 amp versions. So this is intended in an R&D lab to sit and power an entire rack and measure what's happening. And at the top, we have our IEC PAM, as we call it. So this is for single-phase devices for standard servers, for instance, or for anything up to white goods in your canteen. They work with a very wide frequency and voltage ranges. So 3-phase PAM, for instance, we've used in things like 3-phase motor controls, as well as just regular US and EU mains levels. So we can measure voltage, current, power factor, frequency, all the standard things you would need to understand exactly what your mains device are using. And we've got a very high capture rate. So in this case, we've got 8 kilosamples per second. And again, this is a plug and play device. Most mains measurement devices you'll find either require a current probe to go around the cable, which means splitting the cable out, or it requires heavy duty mains wires to be bolted into terminals on the back, which is a pretty complex process, and there is safety elements around that as well. So this is the main hardware. What we're going to look at next is the software and the actual data that we can get out. But in the meantime, are there any questions that come up on the product level? If there isn't at the moment, please feel free just to type into the chat, and we'll get them as we come along. So one of the really key things that we had around this product range was the ability to capture data and view it. And something we're very proud of is Quarch Power Studio. So it's one of the 2 major ways we have of getting data out of this unit. One is automation that we'll look at later, where you pull the data out directly yourself and process it. However, what we discovered is that being able to see both an overview of what's happening and zoom into the smallest detail is incredibly valuable. So this is Power Studio set up with a 2-channel PAM. It would look exactly the same regardless of which of our devices you're using. The only difference will be the number of channels, whether analog or digital, that it's displaying. So this is a 9-second capture at 4 microsecond sampling. So this is us looking at the spin up of a hard disk drive. So you can see on the timeline view in the bottom, we get an overview of everything that's happening, and we've zoomed into the major section in the middle. We've also got some annotations added, which have been added manually later, which can help with analysis just to show what's actually going on. Now, the interesting thing is here, from this zoomed out view, we can then zoom right in and view the smallest detail. We can look at this little ripple here that's come into the voltage rail. We can measure it. See, it's almost exactly 176 microseconds long. This is just a small element I picked on here, but it just shows you how it's possible to zoom right in and look at the smaller elements. And for long-term recording, so if you have a scope and current probes, you are going to be quite limited in terms of resolution and time. Here, we're looking at a 30+ hour automated workload. So what we've been doing here is running a capture of while we are running many different workloads onto an SSD. This was actually fully automated using one of our power versus performance scripts. So what we've done is we've used FIO to run lots of different workloads. We've been varying block size, queue depth, read-write percentages, and similar. We've automatically dropped down the annotations at the start and the end of each workload. We have also added on to here the megabytes per second and IOPS outputs from FIO as a custom channel. So within Power Studio, you can via our automation API, you can add custom channels and add data to it, and you can add annotations. What that means is you can come back in the morning after a test that's run overnight, and you have a full analysis data set ready to look at and understand what's happened. So this is another example we've got here. This is a slightly smaller test, but in this case, we have been iterating through each of the different power states on an SSD. And then plotting the megabytes per second performance onto the chart at the same time as the power consumption. For instance, if you were interested in your drive temperature, you could add a temperature channel on here as well and plot that. What's particularly interesting in this case is as this drive goes through the three different active states, so we've got power state 0, 1, and 2 visible in the middle of the screen here, we can see the power consumption goes down and the performance also drops. One interesting thing is that the performance drops significantly more than the power consumption. So yes, your device, if it goes into a sleep state, your laptop will last a bit longer, maybe to let you see the remnants of that video. However, if you were trying to, for instance, copy a file before you run out of power, the lower power state will actually be worse in this case. And interestingly here, when we go into power state 2, the drive actually cycles between on and off every 2 or 3 seconds. So again, we're going to see a very poor latency if the drive keeps basically shutting itself down for a second or two at a time. It really impacts performance. And the fact you can see this in a really clear visual way really adds to that. Now, what we've also got in the bottom here is we've seen the capture of the LED. So we can actually see that the LED pattern on this drive on the final power state has actually changed. Now, one thing we can pull out of Power Studio as well, once we've dropped these annotations to mark the start and end points, is we can get statistics between them. And that's very valuable in something like a power versus performance test, because you can run your dozens or maybe even hundreds of workloads overnight. You can come back in the morning and then you can order based on the element you're most interested in. It might be, well, what was the worst case power consumption? It might be which workloads had the highest power consumption in comparison to the megabytes per second throughput that they actually got. And being able to gain this data out very quickly like this, we think is very valuable. Another major benefit of the PAM is the fact that we are able to capture the major digital sidebands. So for instance, you can see when your host is asserting burst in relation to a hot plug and how many times. So this example here, we've got, I believe it was a graphics card powering up on boot, and we can see that burst is being asserted 3 times and for different periods of time. So with this, we can easily pull out the markers on the chart. We can measure the gaps between burst and how long the assertions were, and we can decide whether the system is working as intended or whether there was a problem there that we need to look at. The next one, this is another PAM example. So these 2 traces were 2 of the first ever PAM traces that we captured. And another thing that we really notice is that every time you take a trace like this and you get this amount of detail in front of your eyes, it adds questions. People look at things and go, why is that happening? And that really helps you understand what's going on. In this case, for instance, the question is, well, why is our 3.3 volt rail chirping back up and down multiple times? Now, what's happened here is that we have switched off the power supply at the wall. The power supply is obviously trying to jump back up and restart again, and we're getting these spikes of voltage. An interesting thing underneath it is that the wake signal is changing state each time that happens. Now, this might not be a problem. On the other hand, you can imagine a circumstance where a drive that is effectively in a power loss state is being told to change its wake state. That could be a significant problem. And again, being able to see that so easily here is very useful. It's a similar view in the AC world. You don't often get to see this amount of detail in AC. A lot of AC measurements will be second by second outputs on a power delivery controller or similar that will tell you roughly how much power you're using. Here we have got a capture of a compressor spin down. So we pulled power on the compressor, and we can actually see the voltage is not just decaying, it's actually the frequency is slowing. So what we're actually seeing here is back EMF. We're actually generating a voltage from the motor spinning and slowing down. Now this looks pretty clean. The RMS voltage in the brown is slowly decaying away. That looks quite clean. You can imagine a scenario, however, perhaps when you lose power, that there is a sudden spike of voltage that jumps up. And maybe that would explain why your products have a lower life in the field. We're seeing actually damage to components due to a high voltage spike if that was to exist. Another example here, this is a three-phase motor capture across a range of speeds. So we're actually looking at how the three different phases interact to each other as at the start of the graph as the motor is speeding up. So the big yellow section there is basically the voltage going on. But what we're seeing at the edges is significant spikes of current. So basically this device is doing slightly unusual things at the lowest speeds. And that's going to be very valuable information to anyone who's trying to work with this kind of device. Now, I realize in the storage world that most of you are, compressors are probably less likely to be interesting. However, it's a very nice capture here. What is probably more interesting is things like power factor. How is your current out of phase from your voltage? So this is a capture of an extreme power factor. So sort of thing that you might get on a switcher regulator on a server, where you get very sharp spikes in current that are not in phase with your voltage. Of course, if you're running thousands of these in a data center, that can be very significant. Talking of data centers, this is an inrush peak on a 1U rack server. So again, you could put a simple power monitor on the back of the server and you can see roughly what it's doing. Here, what we can see though, for instance, is we get a 4 kilowatt instantaneous peak. As we plug it in, the period of time it lasts for is fairly short. The white markers here are only just over 100 milliseconds apart. At an RMS level, that's peaking about 900 watts RMS. But again, we can see exactly what that server is doing in terms of inrush, and therefore calculate how racks of servers coming up all at once. What's that going to do in terms of inrush? How fast, in terms of recovering a data center or bringing it up, how quickly can we bring up banks of servers? This kind of detailed information could make a substantial difference in planning for that kind of event. Obviously, when you give engineers measurement equipment, they want to measure interesting things. So this is the measurement of power consumption on making a latte. So one of the questions one of our engineers had was, what was better, making a latte or making a cappuccino with a coffee machine? And it's a simple example, but again, it's understanding that you can get detailed capture of pretty much anything that consumes energy. And if you can do that, you then have a chance of actually working out how to reduce your power consumption overall. Now, we've got a very specific example here for customers that I'd like to go through. So I've shown you lots of pretty pictures there. And one of the reasons that we think this is very valuable comes down to this. Sharing scope traces can be pretty tricky, and it is not unusual at all for us to get something like this. So in the top right, this is what we were sent from a customer. It's a phone screenshot of a scope trace with a line drawn around it and scribbled on. Basically, the customer is indicating that they did not like the fact our power trace was different from theirs. So basically what they were seeing on their scope was this very low resolution trace in the top right, which is basically a relatively flat topped block. And we were giving them something quite different. And the question was why? So after a significant amount of work, we got to understanding what was going on, and this is just a brief description of that. So what we can see here in the bottom left is a QPS capture, a high resolution of that spin up. It's the same one we saw earlier, and the HCD engineer explained to us that this initial block of power consumption here is a head alignment process where the drive spins for a period of time and then stops. There's then a main spin up sequence, and when the disk at speed, we then have some spikes at the end as the head starts moving around. Now, the interesting thing here is, so their problem was that our trace was apparently had this power consumption dropping through the period, whereas theirs was quite flat. And a really important thing around here is sampling time and averaging windows. So the OCP spec, for instance, was written heavily around the abilities of the Quarch PPM at the time, actually. So 4 microsecond sampling. And then they placed in the spec an averaging window around that of 100 microseconds to 100 milliseconds, depending on what's happening. And that window choice is incredibly important. So on the left-hand side, we have a raw 4 microsecond capture. On the right-hand side, I've used a 10 millisecond averaging here. But the point is, as soon as we start putting an averaging window across our data, we can see a complete change in the profile. And many of the regions look roughly the same, but the main section, instead of dropping and flattening out, we see is actually increasing in power consumption on the right-hand side. So they look very different, but they're actually not. What we're looking at here, as it turns out, if we zoom right in on the trace, we can start to see more detail. This HDD is pulling power in basically the modulated form. It looks a bit like a PWM signal. So what we've done is we've zoomed in here to 3 different points in the spin-up sequence, and we can see in the first window, we're sitting at a relatively low power state with occasional spikes up. In the center window, we are spending a lot more time spiking up to the higher power state, and by the time we go to the right-hand window towards the end of the spin-up, we're spending most of our time in the higher power state, and we're occasionally dropping down again. Now, that's completely invisible on the scope trace. There simply wasn't enough resolution to show that at all. And even in the QPS trace, you need to actually zoom in or add an averaging window across the top to really understand what's going on. But basically, the customer was being misled over how much power the drive was pulling at what times and what shape the power profile was. And the output of this is that a single scope capture is not enough to analyze power. You need to be able to capture at a high rate. You need to be able to capture a lot of data, and you need the ability to change your averaging or post-process it as necessary to really understand what's going on. Do we have any questions on the pictures? There's nothing in the list at the moment. If you have questions, please do type them into the chat. I'm very happy to cover more things or different things if people have preferences. So we'll move on. So as Gen 5 came along, we started looking at some new features. So there's a couple of reasons for this. One was terms of losses for Gen 5. So in Gen 4, a lot of our customers would stick an adapter board or two in between things to get between maybe the slot that they were testing in and the drive they wanted. At Gen 5, adapter boards start getting very tricky. We want absolute minimum number of items in the path, especially when we're adding test equipment. So this is one of our new products. This is an AIC to U.2 breaker module. So this allows us to do hot swap and physical air fault injection into a U.2 drive that is plugged directly into an AIC slot. So that means you don't need an AIC to U.2 adapter in there as well. The benefit of this on terms of the power side is that we put a PPM injection port onto this as well. So by default, you plug this into your system, the drive will be powered off the host, and everything will just work. However, if you plug a programmable power module into the injection port, well, then you have measurement and power margining directly on there without having to put a separate power injection fixture in between as well. We've done the same thing with a with an MCIO format. So this is going from MCIO cables. So this is intended to go from something like a serial cables host card if you don't have your own Gen 5 system ready. You can test with this. Again, we've got the PPM injection port, so we can take over, supply power to the drive and measure it as well. Then the latest one that we are just about to release, this is AIC to EDSFF. Again, this is formatted as a breaker module, so we've got switches on every pin of the connector, including all the high-speed lanes. So we can do lane reduction, we can do physical air fault injection, we can kill ref clock, all these sorts of things. We can pull down purse to reset the drive. But we've also placed a PAM mezzanine slot onto here. So the idea will be that you can upgrade this later by putting one of our standard power capture mezzanines on here, and it will turn it into a full power analysis module as well. So then, once again, you will be able to both capture the power consumption of your drive, but also view what the digital sidebands are doing, and again, while you are performing a hot plug or injecting faults. So this is us trying to bring together both of our major product lines, and again, make it easier to get power monitoring into products in a way that doesn't require us to put extra interposers into the system.
Hey, Andy, this is Josh again. We have one question of what's the difference between the PAM and the PPM besides PPM supplying power?
So that is the biggest difference. The PAM is a more recent design. It is more modular, as I said, so it can take multiple different power rails. So for instance, our AIC PAM fixture measures 3 different rails. So it has the 12 volts, 3V3 and 3V3 aux. Whereas if you use a PPM fixture, you would the 2 3V3 rails would be shorted together, and you'd be powering both of them from the single 3V3 output of the PPM. So the PAM is more flexible. It's significantly faster for streaming as well. We can stream at 4 microseconds for a lot longer without saturating our RAM. So it is a more advanced device. We are actually working on a major upgrade in terms of software for the PPM that will bring it up to the PAM standards. So the PPM is a product that came out 5 or 6 years ago, but we are still supporting it in full and upgrading it. So we're going to significantly increase its low current performance, for instance, with this update. But the main difference is that the PAM does not supply power, but the PAM can capture digital sidebands. So if you are not interested in doing active power tests on your drive, sort of margining, ramping, glitching, and similar, you would generally be better off with a PAM. You will get more useful capture features, and it will be slightly cheaper. If you want to do active power testing, like your glitches and brownout and similar testing, then you will need a PPM. So the next thing is automation. Quarch has always been about simple automation wherever possible. Now, Power Studio is a great tool for sitting there and viewing things. We think it's very valuable, but we don't want people sitting there pressing buttons. We want them to get immediate access. You want to hit go and come back and then get access to the data later when they want it. So we have a Python package. We primarily write for Python 3, but we do try to support Python 2 as well. Commands for automation are generally very simple. There are multiple examples on our website. This is just a very simple example, choosing a module, connecting to it, and doing a power up, power down cycle. Very simple. There are 2 major methods of automation. One is that you can automate Power Studio itself. So for instance, from a script, you can open Power Studio, you can start and stop your capture, you can send commands to the module, so whether that be setting different voltage levels or changing your output mode or similar. You can start a stream capturing data. You can then download that data directly to a CSV file and do your own post-processing on it, all within the same automation script. You can download or capture statistics tables. So if you've added annotations, you can get direct access to the statistics as well. You can add annotation and comments. You can add and populate custom data channels. And then at the end of this test, you're going to have both a full analysis file that you can open up again and look through. And if you want, you are going to have your raw data in CSV form or statistics that you've extracted and done your own processing or data logging on. If you don't want the graphical element at all, you can throw Power Studio away and you can automate directly at the layer underneath, which is called the Quarch instrument server. So Quiz is again, it's a Java app. However, it will work on a non-graphical system, so it does not require a GUI. Again, we can start and stop capture. We can send commands to the module. We can download the data in a CSV form. What we lose because we don't have Power Studio is we don't have the automatic statistics. So you'd have to do that in your own post-processing. And we obviously don't have annotations and comments and custom data channels because we don't have an analysis file. You're pulling the data out yourself and doing what you want with it. But these two options give you a very powerful range of automation, and you always, regardless of what you choose, you have access to the raw data in full. Although be aware that can be extremely large amounts of raw data if you are talking about 4 microsecond sampling over a long period of time. In terms of application notes, we've got a range of notes on our website. So Power Studio is free to download. Quarch, generally speaking, works by selling hardware, and the vast majority of our software is provided free of charge. So that includes Quiz, Power Studio, and all the application notes that go with it. So for instance, we have application notes to show the basic control of Power modules. We have automation with Power Studio. We've got integration examples of using things like FIO and iometer with Power Studio. So this is creating custom channels and similar. We've got the basics of QPS automation and post-processing. So this is capturing with QPS, but then exporting to CSV and running additional post-process resampling. And then we've got some examples of generating patterns on a PPM. So in this case, I think we're creating basically a nasty series of glitches on top of a DC level that then get injected into the drive. As well as the generally Python-based application examples we do also have a tool called Quarch Compliance Suite. This is the only piece of software that we actually sell, but it does have some free tests in it, so you can download and try out a couple of the initial tests today. So this includes the basic hot swap test, for instance. So anyone who's been to an NVMe Plugfest event at the University of New Hampshire with an NVMe drive will have gone through our hot plug test, where we have to do a range of different hot plug cycles on a drive, from a very fast hot plug to a slow hot plug, verifying the drive comes up every time. So that test, for instance, is free to run on Quarch Compliance Suite. But we have some more advanced tests as well, which are licensed, although it's a very reasonable cost at the moment. So our power versus performance analysis test is one of those. So this is running the 100 or so different workloads on the drive and getting a detailed report out at the end of how it works. We have also things like PCIe lane reduction. So can we bring up a drive in every different lane width that it's supposed to support, and will it work in each case? So with QCS, you get a live report of what's happening. So here we can see we're working through all the different block sizes and a power versus performance test. And then the output of that is a series of checkpoint results and a PDF report, which we now have some both results tables and some nice graphs now when it comes to power versus performance. Now the idea of QCS is many of you will be well on top of automation. You'll have your own automation frameworks and a lot of effort going into that. Not everyone will, though. We find that some of our customers, especially those outside the US, may not have the time or the ability to do their own automation. So we wanted to provide some basic tools to get at least some initial quick tests done with a couple of clicks to get started without having to do significant coding, and that's where Quarch Compliance Suite can be a benefit to you. And that, I think, takes us pretty much to the end. So I hope that was useful. And do we have any other questions? Is there anything else through from your side, Josh?
I don't think so. If anybody has any questions, just I think you have to unmute yourself to ask, or you can just type them into the chat window or the questions window, and we can address them.
Yeah. Now, what tends to happen, of course, is there's lots of questions come up 10 minutes later after we end. So please, you jump on the website, either go to quarch.com email support@quarch.com, email Josh, the guys at Serial Cables, if they're more local to you. We have Lee Hayashida, who's our senior FAE, who's based in California as well, who is in your time zone. So questions that come up, evaluation equipment that you want to try, please get in touch and we'll be happy to help you. Even if it's just you want a general chat about our analysis, even if it's not specifically around our equipment, we're always happy to have a conversation over what you're doing and what might be of use to you.
Yeah, and anybody US based, if you have questions about Serial Cable or about Quarch, Serial Cables represents Quarch here in the US, and either I or Lee can help with anything that you need.
Right, so if there's no more questions, I think we'll call it in and just thank you everyone for coming.
Yeah, well, I guess we'll just wrap it up. Thank you everyone for attending, and thank you, Andy, for your excellent presentation.
Great, thanks Josh for organizing, and yeah, well, I hope to speak to some of you soon.
All right, thanks guys.